Following the ideal gas equation, we have what we call the heat equation. Heat equation measures the amount of heat going into or taken out of a substance to change its temperature. Okay, so in the heat equation, we have Q representing the quantity of heat, the amount of heat we want to put in the substance or take out of the substance. And we say in this formula that's equal to the mass times the specific heat represented by this letter C times delta T, which represents change in temperature. Now let me explain why each of these quantities are involved in the heat equation. Of course, Q represents the amount of heat. I like to use the analogy, or I like to use the example of putting something on the stove, right? Q, amount of heat, represents the amount of heat we want to get from the stove, which represents how long we want to put the thing on the stove. Okay, so if we have more water in a pan rather than less water in a pan, we're going to have to leave it on the stove longer to heat up more water, right? And we're going to have to use more heat to make it boil than if we just want to warm it up, right? That makes sense, right? And the C, well, that's something that measures how hard or how easy it is to knock those molecules around in the substance. It's kind of like, if you have like these big guys, they're harder to knock around. They would take more effort to knock them around than some little guys. So the larger molecules require more heat to get them riled up than the smaller molecules. But in the case of water, I brought up the example of water. Even though the molecules of water are small, they attract each other so much, so strongly, that it takes, the water is able to absorb more heat. It takes more heat to get water to get going, to heat up, especially to boil. Also, right, I mentioned it also represents the amount of heat you want to take out of a substance. So, say I'm working at a convenience store, I might want to calculate how long it's going to take for a case of Coke to cool down in a cooler. I know the temperature of the cooler and how cold, the customers like to have their Coke, how long it's going to take to get, say, a whole case of Coke. Calculate, how much Coke is that? And figure out what the specific heat for Coke is, probably close to water, probably something around there. And it comes in at room temperature. It gets cooled down to whatever we have the refrigerator set at. And I just, put those numbers in, calculate, and I get the amount of heat it looks like we'll be taking out of those little bottles of Coke, and decide how long it would take to remove that heat. So anyway, so we have the heat equation. Say we wanted to solve for mass. See what's the mass in terms of specific heat, temperature, and quantity of heat? Well, here with a little algebraic manipulation, we divide M's partners by Q. And for C, we solve for C, we divide C's partners by Q. So C equals M delta T, right? Over on this side, right, we have the C missing because we're solving for C. Over here up here we have the M missing because we're solving for M. So we take the other two. C is equal to M delta T, M times the change in temperature over Q. And so finally, right, if we wanted to solve for the change of temperature, that would equal to the mass times the specific heat divided by the quantity of heat involved. And that's it. That's so much for the heat equation. All right.